So let's do the consensus for the explosion lab here and see what it really means. Well, remember, here's what we had. We had a little car on a track, and this car had a little spring-loaded plunger right here, and it had a little trigger right here, and then we put it right up against another car. Okay, and it had masses in it. It had a whole bunch of mass in it. And we put these on a track. And you exploded them. That is, you push this little trigger in, this spring came out, it pushed on this car. Let's call this car A and this car B. Car A pushed on car B, and car B moved to the right. But car B pushed on car A. Remember, for every force there's an equal and opposite force, and so car A moved to the left. And what we did is we put barriers on the ends of the track, and we arranged an initial position so that these two cars would hit the tracks at the same time. They would hit the ends over here at the same time. Now, first of all, when you triggered this, the force, this is the force on car B, and let me hold on, let me write underneath it. So car B felt a force, and car A felt an equal but opposite force, right? They're pushing on each other with equal and opposite forces. That's Newton's third law. And so we say the force on car A was equal, but in the opposite direction to the force on car B. Now, because they are in contact with each other, these forces apply for the same little duration of time, a little tiny duration of time. We'll call that delta t. So the force times the time on this is equal, but in the opposite direction to the force times the time on car B. Now, the impulse momentum theorem tells us, so wait, this depends on two theorems. One of it is Newton's third law. We're saying this is true. And then another theorem we're going to use is, hey, force times time is impulse, and impulse is a change in momentum. So this represents the change in momentum of car A. Must be equal, but in the opposite direction to the change in momentum on car B. Well, the masses don't change, and momentum is mass times velocity. So a change in momentum is the mass of A times the change in velocity for A. So this is the chain of logic that we're following here that's based on our theories on how forces work and how momentum and impulse are related. And then we said, well, look, the velocity of these cars. Now, here's our big simplifying assumption for this lab. We assumed that the velocity of car B and the velocity of car A essentially did not change, that friction was negligible, and so that these velocities, the velocity of A and the velocity of B, were going to be the same velocity. The initial velocity was 0. The final velocity of car A was going to stay constant until it hit the end of this track. So we're going to say that this velocity was equal to delta x for A divided by delta t. Thank you. Thank you. And this was the mass of B times delta x, well, let's put a negative there, for B over delta t. So we said that, hey, this velocity, once it's moving, the velocity is going to be constant. So this velocity is just going to be delta x divided by delta t. And this is going to be this delta x divided by delta t. But we arranged the starting position so that they hit the ends of the track at the same time, for the same time interval. So this delta x and this delta x were the same, and we canceled it out. And so this gave us a prediction. We said that if all of this is true, MA delta XA should be equal to negative MB delta XB. So our theories are making a prediction. If we arrange an experiment like this, this should happen. And then you did the experiment. And what you found is that when we took this, let's call this A and this just B, this product and this product, when we went, let's kind of move over here so it stay on the screen, everything. When we said the percentage difference from A, that B is from A, we just said, well, let's A minus B divided by A times 100%. And I think the typical class value, looking around, like you guys got 9%, you guys got 2.5%. We had one group with 0.5% error. I mean, really, really accurate. If you kind of add them all up and average them, it's probably about, I don't know, let's just say roughly 5% different. That when I did this on class A, it was within 5%. That's good. That's pretty good agreement, considering that there is friction and there are errors. There is also imprecision of measurement, uncertainty in our measurements. So I would say, hey, it's kind of like Mythbusters, right? You guys watch Mythbusters, right? You got three options, right? You got confirmed, plausible, and busted. And certainly this percentage difference, I mean, these are close. So it's certainly not busted. I would say at least plausible, but I'm here to tell you as a physics teacher, it's this is right. And these percentage differences are because we're people, we make mistakes, our measuring tools are not perfect. This is very close. Okay, so we can say that Newton's third law, that for every force on one object, there's an equal and opposite force on another object, is confirmed. We can say that the impulse momentum theorem is confirmed. Also, how much momentum was there before? Well, let's take this, and this will be the last thing. If I take this and say the change in momentum of car A, and then add this to both sides, I get plus the change in momentum of car B is equal to 0. So if I say, okay, this is how much the momentum of car A got changed, and this is how much the momentum of car B got changed, when I add those changes together, I get 0. What that means is that there's no change in momentum of our system. Here's our system, these two cars, and we're saying that the momentum of my system before the explosion is equal to the momentum of the collision after the explosion. This 0 equals 0. Okay? And remember that momentum is a vector, and that's why, yeah, car A gets momentum. Car A starts off with no momentum at all. It's not moving, but then it moves to the left. Car B moves to the right, but they have the same amount of momentum, but in opposite directions. So when you add them together, you get 0. That is all.